Hello everyone, myself Adav Sarthak and my team members Pooja Chaudhary, Ganesh Gaikwad and Chaitali Kanwade are going to present a presentation on the state feedback controller for DC motor under the guidance of Professor Dr. G. Vijay Kumar. So let's start. Why we use state feedback control in the system? First is improved stability. It helps in placing the system poles at designed location and ensure the stability. Second, faster response. The controller allows adjustment of transient response, reducing rise time and settling time. Third, reduce overshoot. It minimizes the unwanted oscillations and overshoots in the system response. The next is uh, better control over multiple states. Unlike traditional PID control, which use only error signals, state feedback control consider all state variable improving system accuracy. The next is optimal performance with techniques like LQR, linear quadratic regulator. States feedback control can provide optimal performance with minimum control effects. Thank you.
So hello everyone, my name is Chaudhary Pooja Arun and today I am going to explain you the MATLAB program designing for a state feedback control system for a DC motor using a pole placement. It ensures that the motor meets desired performance characteristics like overshoot and settling time. So let's break it down step by step. So this MATLAB designing is demonstrate the design of a state feedback control for a DC motor system. Firstly, here we are using a clear and close all for clearing all the data from previous editor field. Then secondly, here we are defining some motor parameters like R, which is given as 0.5, which is armature resistance. L is given as armature inductance 0.2 Henry. Here KT as a top constant given as 0.929. KB back EMF constant. J is using for moment of inertia. B used for friction constant and B for armature voltage. These parameters are used to model the motor's dynamics. In second slot, state space model of DC motor. In this, here we define 4 matrix for 4 gain of block, which we are used in model system. First matrix here we given it for a system matrix. Second one it is given for input matrix, and third matrix we give it for output matrix, and fourth one as D is equals to 0 we given for it a direct transmission. In a third concept, this represents the system dynamic, which is at dx by dt is equals to ax plus bu, and for y initial it is a cx plus of du, where x is a current speed and which are state variables. In third, we are using initial condition and stability check also. Here we give 2 parameters as x0, which is an arbitrary initial condition in a 0 current and -1 radian per second speed, and where E, which defined for eigenvalues of eigen A, which is in check in open loop poles to assess natural stability. In fourth condition, here we are given as the check controllability, where QC is equals to CTRB, which is command as A and B axis computes the controllability of a matrix. And second part is rank QC, which verifies the system fully controllable, where rank is equals to 2 for this 2 state of system.
I'm Chaitali and I'm explaining the code for the state feedback control design. Then desired pole displacement. The desired closed loop pole locations are determined based on the roll number, that is the maximum overshoot 33%, and the settling time TS is equals to 17 seconds. From these specifications, damping ratio is calculated from the overshoot. Natural frequency omega n is calculated from settling time and zeta. The desired characteristics polynomials roots are computed. Reference step response. A reference second order system with the desired characteristics is created, that is G is equals to TF num 10, and its step response is plotted to verify the specifications. Then state feedback design. K is equals to place A, B, P, computes the state feedback gain matrix K that places the closed loop poles at the desired locations P. The closed loop system becomes A minus B into K. Then the simulation. The system response to initial conditions is simulated. Then there are two plots which are current response over time and the speed response over time. The responses should exhibit the specified overshoot 33% and settling time 17 seconds.
Hello guys, I am Ganesh Gaikwad. Today I am going to explain you the state feedback control simulation model on a MATLAB Simulink, where we want 4 gains, 1 integrator and 1 summing point for this, and also scope for the seeing output. So let's start. First of all, search for a gain. Make a copy of this gain. Flip 2 gains for the system matrix and feedback loop. Make a copy of this. So search for integrator. We are using this integrator for the initial condition. Search for summing point. And most important thing, that is the scope, where we can see the output of our given model. So we want to give name to the all blocks. So first block we are using for the input matrix. This input matrix we are denoted by the B in our program. So here we are adding the capital B. Then see, here the capital B value appear automatically, and the multiplication we are choosing this for element wise K multiplied by U. Apply, then OK. For integrator we are using this for initial condition. For initial condition we are using X multiplied by 0. So the value of x0 is appeared here automatically, 0 and -1. Apply, then OK. Now give the name initial condition. Then we are using this gain for the output matrix. So give name output matrix. And the output matrix gain is denoted by the C in our program. The values appeared automatically like previous. Now change the multiplication from element wise to matrix K multiplied by U and U vector. Then apply and press OK. Then this gain we are using for the system matrix. So give name system matrix. And system matrix we are denoting by the A. So type capital A and see the values automatically appeared here. The multiplication is changed from element wise to matrix K multiplied by U and U vector. Apply and OK. Now at last we are using this gain for a feedback gain. So give name feedback gain. Then the feedback gain is denoted by minus k in our program. So give the minus capital K. See here the value are automatically appeared. And the multiplication also changes from element wise to matrix K multiplied by U and U vector. Then apply and OK. Now connect properly all blocks to each other. So first of all, connect the initial condition to the output matrix, and feedback gain is connected before the output matrix, and system matrix also connected here. Now another point of system matrix is connected to the summing point, then another summing point is connected to the input matrix, and the output of summing point is connected to the initial condition integral matrix. Now the input matrix is connected to the feedback gain, and at last we are connected output matrix to the scope or the output waveform. Now we are giving the stops time to multiplied by d, because d we are defined in our program previously. So this is our model for the state feedback control of a DC motor. Then run the simulation. Now see our output is accurate. So thank you guys.
So now I am going to explain about the results, that is the graphs. So the first graph is response of current to initial condition. The graph shows how the system current evolves over time when given an initial condition. The waveform indicates an underdamped response, meaning the system has oscillation before settling. The initial current peaks, then oscillates, and then finally stabilizes after some time. The system may have damping, but it's not critically damped, as small oscillations are still visible. So the next graph is response of current to initial condition and response of speed to initial condition, that is current and speed response to initial condition. The top graph shows that similar to the first graph we have looked. It shows an overshoot followed by oscillation before reaching a steady state. The bottom graph, that is speed response. This shows how the system speed responds to initial condition. The both graphs indicates a second order system which state feedback control can improve. So the graph is step response. This system is given to step input, then its response is plotted. There an overshoot which indicates that without feedback control the system has tendency to excite the desired value before settling. The system exhibits damping and oscillation before stabilizing, showing it is not critically damped. Thank you.